Yes. So it's not a hard question. So just do try your best in the cards, the assignments, and so on and so forth, so that you don't have to get any retake as long as you're serious with your work. Okay. Okay. Chapter 3, critical systems specification. Okay. So under this, our objectives explain how dependability requirements may be identified by analyzing the risks faced by critical systems. Okay, we're going to analyze the risks. We're going to see how you can find out dependability requirements. Remember, dependability involves, as we said, availability, reliability, safety, security. Okay, to explain our safety requirements are generated of your dependability requirements, among which we also have safety requirements. Explain the derivation of security requirements and to describe metrics used for shall look at the first two, and then on so next week we shall. The topics we're going to cover here involve risk-driven specification, safety specification, security specification, and software reliability specification. Okay. Okay, so before, yeah, I just forgot, before I get further into this, last time I was sharing with you on the risk, let me open that textbook from Nancy Leverson on how the industry is changing. Okay, on how the industry is changing and on how the risks are also, the way they are affected is being changed also. Okay, we had looked at some points. I just want to look at the rest of the points. Okay, if you go to Nancy Leverson, it will be page 8 downwards. The unique risk factors in the industrialized society. And so the factors we're looking at are the ones that affect this risk, okay, and how it's all changing, okay, and how it's all changing. We had seen the appearance of new hazards. We had seen the increasing complexity. We had seen someone actually I shared with you this textbook. So, yeah. I think you can see the text I'm talking about. Before each how factors that affect risk are different. Okay, they keep on changing. I believe you have the textbook. Let me just put back the other. Yeah, so I believe you have the textbook. That's the one which I'm referring to. Okay. And the part I'm talking about right now is the one that says that risk is a combination of the likelihood of an accident and the severity of the potential consequences. How's this coming on my screen? Of So risk increases if either the likelihood or the magnitude of losses increases, okay? And different factors may affect these two components of risk. So now this is the factors I'm talking about. These are the factors that affect these two components of risks that I'm talking about, okay? The likelihood of an accident and the severity of the potential consequences. Okay, and remember that risk increases if either the likelihood or the magnitude of loss increases. Yes, the last time we had talked about a few of them. Just a second, let me just try to access something here on my phone. Yes, last time we talked about the fact that it's not the same as in the past now. The factors that you have that are affecting risk now are not the same as the ones in the past. Okay, last time I mentioned about the appearance of new hazards. There are new hazards now that were not there in the past. I also talked about increased complexity. It's not the same complexity now as in the past, okay, because of how the systems are changing. Increasing exposure, you have a huge population now compared to the past. So you're not having the same the same number of people being exposed to the same risk. Okay, talked about increasing amounts of energy last time. The amount of energy being dealt with now is very different, and it's much higher than what was. Okay, so still going on in that same direction is the increasing automation of manual operations. Okay, I hope you have that textbook. Okay? Do you have that textbook? I hope you have the text. You can respond on the chat. I hope you have the textbook. If you don't have, you can just consult with Omar. He has it. Okay. So anyway, the increasing automation of manual operations. So you see, in the past, there were very many manual operations. Okay, yes, you have it. There were very many manual operations, and this is in industries. This is everywhere, really. And right now, you have many of these being taken over. They are control being taken over using software. But there's a disadvantage in this, and there's a very good example that they give here in that very book about a China Airlines flight that had a loss of power in one of its engines. However, because of the autopilot, they could not notice this loss of power in the engine. Only autopilot runs the plane on its own. So the autopilot was compensating for the loss of power in this engine. So the engine is a manual operation. The autopilot is a system that removes the manual operation of the engine. You can't maneuver the plane manually. If it's in autopilot, it's really like on a free, should I say like free fall? It's moving on its own. So by the time the engine completely lost its ability and the autopilot could no longer compensate for it, it was too late. And the plane nosedived over 30,000 feet, okay, and crashed to the ground. So that gives you a picture of how the automation that is coming in of so many systems increases risk. It affects risk. Okay, then we also have the increasing centralization and scale. Here, remember, because of this automation, and what happens is that very huge plants, very big plants can be constructed. For example, maybe very big ships, very big submarines, because you have one place where you're going to control them. You don't need to control all of the whole of it manually at each and every point. But that's also a disadvantage, because even as the example they give in the book, the gigantic scales of vessels creates an abstract environment which crews are far removed from direct experience of the sea's unforgiving qualities. So an example here is the ships that were there in the past. They were small enough such that they could be maneuvered, they could be controlled. Maybe the masts, for example, someone to watch over from the top to keep on changing what needs to be changed. However, because of automation, you have bigger ships, bigger submarines coming in, but then you are not looking at the proportion of how the sea is going to affect these is going to affect these ships. Okay, you're not looking at that proportion, because as you increase the size of the ship or the size of the submarine, definitely the sea is going to affect it in a certain way, of which the automation is not the best way to capture that. Manually, it would have been better, but then it's also not really possible, because if something is so big, you cannot control it at each and every point. Okay, so that's what happens. That's what is happening now. We are having increased technology, but then the kind of risk that is there now is different from what was there in the past. Okay, then there is the increasing pace of technological change. Okay, and this one is quite crucial, because look, in the past there are some technologies, for example, now like building a bridge. Building a bridge, if a bridge collapses, you can know that from this point is where the issue was, and so next time we have to do better. Maybe one person has been killed by the collapse of the bridge. But then the kind of technologies we have nowadays, or the kind of systems people are working on nowadays, like atomic energy, you won't have the space of such error, because a small error can cause the annihilation of an entire country. So I hope you see the picture of how the risk is really changing from the past. Okay, you will not have this. You don't have the same space of making error, because you're having much more energy being dealt with. You're having more complex systems that can destroy a single location in just a second. Okay, an atomic bomb can even destroy. It can destroy an entire country. So you're not going to talk about a mistake that can be learned from and then corrected. Okay? It's not like a plane crash, which is going to kill about 300 people. That's also a big number, but it is going to cause such huge damage. Okay, so those are points I wanted you to note in that textbook. They are very interesting and very important points of the kind of how the change in the industry, in the systems that we have also changed the risk. Okay, it's not exactly the same. So let's go back to our topics. Okay, we are going to do risk-driven specification and safety specification for today. Okay. Okay, so before we go into those, they define your dependability requirements. Remember that after doing these specifications, the risk-driven specification, we shall get the dependability requirements, of which I told you that among them we have the safety requirements, which we shall see. For example, we shall see the ones of the insulin pump. Okay, so we just explain what these requirements are. There are different types. We have the functional requirements, which define error checking and recovery facilities and protection against system failures. The non-functional requirements, which define the required reliability and availability of the system, and the excluding requirements that define states and conditions that must not arise. So they just give those definitions really to make you understand better what these requirements are. Okay. Okay, so our first main topic for today, risk-driven specification. So critical system specification should be risk-driven. This means that you know, once you know the risks, then of course you are going to know how you're going to deal with them, and so you will know the safety requirements. Okay. Then you know the safety requirements. Once again, if you have, I hope you all, okay, I know some of you have the textbook. If you just check on page 12. Is it page 12? Let me see. No, sorry, page 6. Hey, so this, no, this is not Leverson, it's now another one. I shared with Oma also another one, which is called chapter, it's just called chapter 12. Okay, chapter 12, safety engineering. It's another PDF I shared. Chapter 12, safety engineering. Okay, so these are some of the ones. So this we shall be referring to them. So it's good if you have them. Okay, so there they just really explain further about the risk-based specification. Okay, they just try to explain it more than they explain here in these PowerPoints. Okay, this approach has been widely used in safety and security critical systems. Okay, remember the aim of the process should be to understand the risks faced by the system. So once you understand the risks, then you're going to define the requirements that reduce the risks. Okay, and it's what they talk about also in the textbook. They say risk-based specification is an approach that has been widely used by safety and security critical systems developers. It focuses on those events that could cause the most damage or that are likely to occur frequently. Events that have only minor consequences or that are extremely rare may be ignored. The risk-based specification process involves understanding the risks faced by the system, discovering their root causes, and generating requirements to manage these risks. And we are going to see, did I share chapter 2? And we are going to see actually that this is the exact thing we're going to do in our the steps for this risk-driven specification. Okay, those are the various steps we are going to take. We are going to understand the risks faced by the system. We are going to discover the root causes, and then we're going to generate requirements. Okay, those will be the exact steps, and that's what they explain here on the next page. Okay. Oma will share. I think maybe I need it shared. We will share. Okay. There are so the stages of risk-based analysis. If you can share now, fine, you can share now also, that will be fine. So the stages of risk-based analysis, we have risk identification. We have risk analysis and classification. We have risk decomposition and risk reduction assessment. Okay, so these, again here, they just really give a brief explanation, but in the textbook, they explain further. Okay. So identifying the potential risks, as it says, risk identification, identify the risks, analysis, assess what's the effect of, how bad is this risk? Okay. Decomposition, what's the root cause? And then reduction assessment, you're going to determine the requirements that are going to be used to remove or reduce the risk. Okay. Okay, I don't know, my computer is a bit slow. Okay, then here it's just simply a diagram view of it. It's a diagram view of it. And still, when you look at that same textbook on page 8, okay, they as I told you, they explain more in detail. I will just show you so that at least when you get the book, you can see. Okay, so they explain more in. Oh, it does not come. Where is it? Okay, yeah, there you go. So they explain more in detail there. Okay, so that they're just the different steps. They explain more there. So when you open those, this will be a very good page to read. Okay, and to read there more detail. That will be helpful. Okay, let me go back to the PPT. Okay, so they explain better risk identification, description. We're already going through that. Assessment is the analysis and classification. The root cause analysis is the decomposition. And then you can get the dependability requirements after that when you're doing your risk reduction assessment. Okay. So our very first step was the risk identification. This is just for further explanation. In safety critical system, the risks are the hazards that can lead to accidents. Okay, that's why you see even in the textbook, they actually talk about hazard identification, hazard this, because the risks are the hazards that can lead to accidents. Okay, so don't get confused by in the textbook, they're saying hazard identification. Here we're saying risk identification. Okay, don't get confused by that. In security critical systems, the risks are the potential attacks on the system. Okay, we shall see the security one next time. So in risk identification, you should identify risk classes and position risks in 3 classes. Okay, so the risks go in different, in these classes, they go in different classes. Service failure, electrical risks, biological hazards. Okay, and here they give you an example of the insulin pump risks. Okay, which we have insulin overdose, insulin underdose, power failure, electrical interference, poor sense and actuator contact, parts of the machine breaking off in the body. Okay, infection. Okay, remember, once this session gets off, please, you can just reconnect back, okay, on the same link. Infection, allergic reaction. So all those are risks of the what? Of the insulin pump. Okay, so now the next stage is risk analysis and classification. Remember what we're looking at? We're looking at, don't forget, we are under risk-driven specification, okay, of which these are stages of risk-based analysis. The first stage was risk identification. The next stage is risk analysis and classification. Okay, so just don't get lost. It shouldn't look. Please have like a general vision, that's like a map, so that you don't just see things for the sake of where they are, but then you know exactly at what point and how to relate to them. Okay, so this process is concerned with understanding the likelihood that a risk will arise and the potential consequences if an accident or an incident should occur. Okay, concerned with understanding the likelihood that a risk will arise and the potential consequences if an accident or an incident should occur. So you can categorize risk in 3 ways. Okay, you can categorize it as intolerable. That means it must never arise or result in an accident. Okay, you can define it as a LAP, that is as low as reasonably practical. There, it must minimize the possibility of, we must minimize the possibility of risk given the cost and schedule constraints. And then also acceptable, whereby the consequences of the risk are acceptable and no extra cost should be incurred to reduce hazard probability. Okay, so looking further into this, you need to carry out this analysis to understand whether a hazard is a serious threat to the system or the environment. Okay, so remember, you're carrying it out to know how serious this risk or this hazard is. Okay. The analysis also provides a basis for deciding on how to manage the risk associated with the hazard. Okay, so because now if you know how dangerous it is, then you are going to know how you're going to manage it. For each hazard, the outcome of the analysis and classification process is a statement of acceptability. This is expressed in terms of risk, where the risk takes into account the likelihood of an accident and its consequences. And then so these three categories we're talking about, beginning with the intolerable risks. So the intolerable risks, these ones here, the ones that threaten human life. Okay, that first category you see there, they threaten human life. Okay, so such hazards, now the system must be designed so that the hazard either doesn't arise, or if it arises, the system will ensure that they are detected before they cause an accident, because it threatens human life. Okay, a very good example is an overdose of insulin. Okay, that's an example of an intolerable. And if I go to this, okay, you can see there, number one, insulin overdose. At the end there, the acceptability is intolerable. Okay, so that's an example of an intolerable risk. So an example of a category of acceptability of risk as being intolerable is an insulin overdose. Excess insulin is actually very dangerous. Okay, it's very dangerous. It causes the body to absorb too much glucose. Okay, and definitely this is dangerous. Some of what can happen once someone has an overdose of insulin, they can be sweating, chills, anxiety, irritability, but then the worst thing that can actually happen is death. That's why I'm saying that intolerable must never arise or result in an accident. Okay, now here we're talking about death. So that's an someone is saying something here. Okay, so someone shared it here. Good. So we're talking about death. Okay, and then for the next category, as low as reasonably practical. Okay, it's about to disconnect. It's just a minute. So these risks, they have less serious consequences. Okay, when you compare it to intolerable, they have less serious consequences, or they are serious, but they have a very low probability of occurrence. Okay, so in this case, the system should be designed so that the probability of an accident arising because of a hazard is minimized. Okay, subject to other considerations such as cost and delivery. An example of an ALAP risk, okay, ALAP is as low as reasonably practical. An example of an ALAP risk, remember our basis for understanding is the insulin pump. That's why I'm giving examples from the insulin pump. Okay, so an example is failure of the hardware monitoring system. Okay, the consequences of this, the worst thing that can happen is a short-term insulin underdose. Okay, a short-term insulin underdose is not that bad. Okay, it wouldn't lead to a serious accident. Someone is saying something here. Oh yeah, Uma just sharing everything. So that's an example of an ALAP from the ALAP category. And then we also have the acceptable category. Okay, so acceptable risks are those where the associated accidents normally result in minor damage. Okay, system designers should take all possible steps to reduce acceptable risks, so long as these do not significantly increase costs, delivery time, or other non-functional system attributes. Okay? For the insulin pump, the example of the acceptable risk, an allergic reaction, okay, arising in the user. So the allergic reaction, it usually causes minor skin irritation. Okay, it's not something dangerous at all. So it will not be worth using special, more expensive materials in the device to reduce this risk. So this risk here shouldn't make someone spend so much money in trying to avoid it, this category. Okay. Okay, right. Now, this diagram here, it's not coming quickly. Yes, this diagram here just shows all these risks. It shows all these risks. There's what we call the unacceptable region. Okay, risk cannot be tolerated. We saw that. Then we've also seen the allowed region. Risks tolerated only if the risk reduction is impractical or grossly expensive. And then we have the acceptable region where we have negligible risk. Okay. Oh, there's something here in this PPT which I wanted to correct. I haven't yet sent it, but good, so I can just correct it now. This was supposed to be downwards. Okay. So this is about the social acceptability of risk. Okay. The acceptability of a risk is determined by human, social, and political considerations. So we have risks, but remember, risks, they also depend on on the location, on the country. For example, you're going to have some risks here in Uganda. They won't be the same risks you have. The same risk you have here is not going to be taken in the same way as in another country, especially if it's outside Africa, for example. Okay, so here they explain that these boundaries, you see these boundaries here? These boundaries, this one and this one, the one they're talking about here. When you see that in most societies, the boundaries between the regions are pushed downwards with time. That is, society is less willing to accept risk. Definitely, when you push this boundary down, and you push this boundary down, you can see that the negligible risk is decreasing. Okay? Whereas the unacceptable or intolerable